Hi viewers, welcome to LMS Solution. Today we are going to see about grid interface to solar PV based water pumping using induction motor. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. So this model consists of grid system as well as solar PV to drive the induction motor, and that induction motor will be act like water pump. Okay, so first I'm going to explain about the grid system. So here you can see that, so here we have grid, single phase grid with amplitude of 325. That means it having 230 volt RMS, and then here we are measuring the voltage and current of this grid side. That means source voltage and source current. And then here we are using the diode rectifier, the single phase diode rectifier. So it going to be convert AC into DC. And then here we are using filter, LC filter, to filter out that ripple in the diode bridge rectifier output. And then here we are using boost converter. This boost converter going to act as here the power factor correction converter for this grid side diode rectifier. Okay, that means, so this power factor correction converter going to be correct the power factor of the source current. That means source, right? That means because we are using diode rectifier here, because of diode rectifier, what will be happen to the source current, right? The source current nature will not be not sinusoidal because of the diode rectifier, that will be act as a non-linear load. Okay, so in order to improve that the source power factors, and then in order to make source current sinusoidal, so here we have used that power factor correction converter. So this power factor correction converter can be controlled by means of control logic. So here we are measuring the source voltage, and then it will be processed via PLL, phase lock loop. This phase lock loop generate unit vector template, nothing but so it will be generate the phase angle with respect to time. Okay, and then here you can see that, so here we are measuring the DC link voltage, right? So this is DC link capacitor. So here we are measuring the DC link voltage, and then process via low pass filter, and then here this DC link voltage compared with the 400, because here we are going to maintain the voltage around 400 here, and then it going to be processed via PA controller. So the PA controller will be generate the reference current in the form of DC quantity. Okay, so here this the reference current going to be multiplied with the unit vector template. That means we are measuring the output of that means PL, right? Phase angle with respect to time going to be converted into sinusoidal form. So by using this block, that means it going to be processed by a sinusoidal block, and then we are getting the sine wave here. That means with the unit that means amplitude of 1, and then we are going to use absolute flux. So here we are converting that sine wave into, that means this kind of sine wave, that is called like rectifier output concept, right? So we are taking only positive value, and then it going to be multiplied with this reference current. Okay, so this is reference current going to be multiplied with this sinusoidal waveform, that means rectifier the output waveform, right? And then it going to be act as a reference current here, right? That means we are going to make this current, right, source current sinusoidal. Okay, so how we are going to make the source and sinusoidal means, here we are generating the reference current. Okay, like this, like rectifier output concept, and then it going to be compared with the current from here, current from that power factor correction converter. So this current will be compared with here. So normally here the waveform is like this, look like this only, right? When you did not use any this power factor converter current, and then you will see that this kind of waveform. So it's not you rectifier output, so it is having some distortion in the system, right? So here we are going to make this current will be like this, you sinusoidal with the rectifier output concept, right? So for that I'm going to, here we are going to compare this reference current with this current, right? So after that we will get the error current. So error current will be processed via PA controller. So here we are generating another component, nothing but we are generating some duty cycle based upon this concept. So here we are taking 1 minus modulus of Vs divided by, sorry, so here taking 1 minus modulus of Vs divided by Vdc. Okay, so it will generate some duty cycle. So this controller also generate duty cycle, so both are is added here, and then here we are getting the controlled voltage in the form of sinusoidal nature. Okay, sinusoidal nature. Okay, so it will be compared with this triangular wave, and then it will generate the pulse for this IGBT, that means pulse for this power factor correction converter. So this pulse going to be control the system in order to make the source current sinusoidal. Okay, so this is the working of this system, that means in grid side system, right? Next we have to move on to solar side system. So solar, here we are using solar panel. Solar panel rating is the single panel rating is 210 watts, and then voltage at maximum power point is 28.7 volt, and then current at maximum power point is 1.32 amps. Okay, and then the total power we are generating from this panel is around 2311 watts at a standard test condition. And then here we are using boost converter. So this boost converter going to be controlled by means of this incremental conductance MPPT. That means we are going to measure the voltage and current of the PV panel, and then going to be processed via INC MPPT, and then going to be processed via PWM generator, because output will be duty cycle. Then going to be processed via PWM generator, and then going to be control this IGBT in order to extract the maximum power from the PV panel. So and then is going to be, that means the output of this boost converter and the output of this power factor correction control is connected at a common DC link. Okay, so this going to be supply the power to the this induction motor. So here we have 3-phase inverter, voltage source inverter, and then here we have 3-phase induction motor. The rating of induction motor is we are using here is 2.2 kVA, and then 230 volt 50 hertz we are using. Okay, and then here we are measuring the speed of the machine, and then here using u square, that means omega square, and then it will be multiplied by the gain unit k, 6.55 into 10 power minus 4, and then is given to the torque input, right? So this concept known as water pumping concept, right? So if you take any water pump, so it going to be related with this kind of equation. So only that means torque which is equal to k into omega square. Okay, and then this inverter, right? So this inverter can be controlled by means of two concepts. So one is here you can see that it can operate in three mode 1, 2 and 3. In mode 1 means there is no power from the grid side, so the grid is switched off condition. That means grid voltage is going to 0 here, right? So grid voltage 0, then we are going to operate this model fully on solar PV power, right? So for that we are generating a reference command. So based upon that PV power, right? So this is mode 1 operation. So mode 2 operation, mode 2 means, for example, you are going to consider there is no power in the PV, right? And then you need to get the supply from that grid alone. So for that we are going to make mode to operation reference command, then win 1430. So 1430 nothing but the rated speed of the induction motor, so that will be given here. So it will be, that means here we are going to make that rated speed of the induction motor always constant. That means we are going to operate this induction motor at a rated condition. So because we are here, we are using that means we are going to drive that induction motor like water pump. So we are going to operate that induction motor at a rated power concept. So that's why we are making that command, reference speed command is 1430, and then it going to be processed via V bar of control, and then we are going to generate the pulse for this inverter. Okay, so now I am going to operate this model at the mode 1 operation. That means here I am going to make peak amplitude equal to 0. That means the system not supplying power to this, and that means grid is not supplying power to the system, and then only the induction motor will drive based upon that power from the that being PV, right? So I am going to simulate this one, and then you can see the different results. So here the source voltage, right? Here you can see the source voltage is 0 and source current 0, because that means for mode 1 I make that peak amplitude which is equal to 0, and then here you can see that this is a PV voltage. Okay, so this is a PV voltage, and then PV current and PV power. So here the irradiation set at 1025 degrees Celsius. So that means maximum power we are getting from that PV is around 2000, right? 2300, right? So is keep on increasing, and then this is a decreasing voltage. So decreasing voltage, you can see that is keep on increase from 0 to nearer to 400, because the decreasing voltage we are maintaining here is 400, right? So, and then here you can see that this is the variation of stator current and the speed of the induction machine, and the electromagnetic torque of the induction machine. Okay, so now the machine is operated fully on the PV power alone, right? So whatever power we are getting from the PV, so that's when we drive the induction motor. Okay, so this response we are getting from that induction motor, and this induction motor is driven based upon this PV power. Okay, so now we can see that the PV attained the maximum power, right? It's around 2300, and then here we have that PV voltage around uh, 300, right? 300, and then here you can see that the PV current is around 7.4 amps, right? So here we are hitting the DC voltage around 410 volt, right? And then here you can see that the torque of the induction machine is maintained at 2 Newton meter, and then here you can see that the current of the machine. So current of the machine is around, the peak current around is uh, 35 amps. Okay, and then this is the speed of the machine. Speed of the machine is around 600 rpm, right? So here we are not that means the system fully controlled based upon the PV power alone, right? So whatever power we are generating, so that will be going to used for drive the induction motor. So this is mode 1 operation. Okay, so next move on to mode 2 operation. So in mode 2 operation, so here you got to make the grid voltage at 325, and then that means PV power equal to 0, right? That means there is no power on the PV, so the power will be taken from the grid alone. So during that time we are going to make the speed command, right? Speed reference speed command to the induction motor is 1430. So the motor will be operated at rated speed. That means it will be operated at 2.2 kV, right? Now I am going to simulate this model. and then I will show you the result of this system. So now is that means you can see that. So this source voltage and source current, the source is supplying power to the induction motor, right? You can see that it starts supplying the current. Okay, the current it's supplying around 15 amps peak, right? Here you can see that the current of PV voltage is 0 and PV current is 0 and then PV power is 0, right? So here you can see that the DC link voltage is maintained around 390 volt, right? So here you can see this is stator current and then speed of the induction machine and the torque of the machine. So here you can zoom this one. So here you can see that the current of the induction machine sinusoidal and then with the peak amplitude of around 12 amps. Okay, and then you can see that the speed of the machine is maintained at around 1380 rpm, right? And then this is the torque of the machine. So torque of the machine is maintained at around 12 newton meter, right? So here what will happen here, we are getting power from the grid. Okay, so because there is no power on the PV, so we are getting power only from the grid. And also you can see that the power factor, right? Here you can see that both are in phase, current and voltage are both are in phase, and also the the nature of the source current is sinusoidal. Okay, so here the power factor is improved in the system. Okay, and also it directed drive the induction motor water pump. Okay, so this is working of the system with the mode 2, right? Mode 2 grid only supplying the power to the induction motor drive for water pump, and solar PV does not have any power. So now I'm going to change this one to 1000. Now both solar PV and the grid will be supplying the power based upon power availability of PV, right? Now I'm going to make here the system power is 1000, that means irradiation equal to 1000, and I'm going to run the model and then I will show you the result. So both are now that means now the PV power, right? Based upon PV power, so we are getting the power from the PV alone, because now PV generating around 2300 watts, right? So it can supply the power to the induction motor. So that's why we are not getting any power from the grid, right? Here you can see that the grid current is nearer to 0. So we are not taking any power from the grid. Okay, we are taking power from the only PV, and then going to supply the power to the induction motor water pump. So now you can see that the stator current, speed, and electromagnetic torque of the induction machine. So now I'm going to change the irradiation, right? So now you can see that the PV operated at 2300 watts. Now I'm going to change the irradiation to 500. Okay, so that we check the result of the system. So after changing the radiation now, so you can see that the power of the PV changed to 150 watts because of change in irradiation from 1000 watts per meter square to 500 watts per meter square. So because of that, power generation from the grid is reduced, right? But we are operating the induction motor at a rated condition. That means we are operating that induction motor water pump at 2.2 kVA. So in order to supply that power, what happened? The source will be supplying the power. Grid will be supplying the remaining power. Okay, so it's supplying around the peak current of nearly 9 amps. Okay, so and also you can see that the nature of the current is sinusoidal, and then the both source voltage and current, right, both are in phase, right? So here the system is operated at that mean unity power factor concept, right? So now again I'm going to increase the, that means decrease the irradiation, right, to 0, right. Next we have to check the response. So here you can see that because of irradiation changes to 0, what happened, grid supplying the maximum power, right, to the induction motor water pump, right. Here you can say there is no changes in the stator current, speed, and electromagnetic torque of the induction machine. So the induction motor water pump continuously getting power from the both PV and grid, so based upon the irradiation of the system. So again I'm going to change to irradiation to 500, and then we will check the result of the system. So now because of increasing radiation, right, the power of the PV is increasing, and then you can see the current sharing, right, current sharing is now decrease, right. Okay, so based upon this radiation, and the induction motors continuously receiving the power. Okay, so this is a working of mode 3. So this is working of grid interface to solar PV based water pumping using induction motor. Thanks for watching your videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.